Let's solve Unit 5 System Software and Operating System questions. Consider the following table about processes, their burst time and arrival time. P1, P2, P3, P4, P5 along with their burst time and arrival time are given in the tabulated form. Now, which of the process shall finish second last as per the respective Gantt charts for the non-preemptive SJF and round robin? When you take round robin algorithm, they have given the time quantum as 10 and we have to find the second last as per non-preemptive SJF and round robin scheduling methods. So let's start with non-preemptive SJF. This is a CPU scheduling algorithm in which the process with the shortest burst time is selected for execution next. And since they have told it's non-preemptive, once a process starts running, it continues until completion without being interrupted by any newly arriving processes. So let's take the Gantt chart here for non-preemptive SJF. Let's take this to be time 0. At arrival time 0, what are the processes available? P1 with 9 burst time, P2 with 30 burst time, P3 with 4 burst time. So here you have to select the shortest job. It is P3. So P3 will start executing. Since they say it is non-preemptive, at the time of completion it will check for the next shortest job to be picked up. Till then it will not be preempted, means this process will not be disturbed. What is the burst time? It is 4. So at 4 P3 will be completed. Now we have arrival time 2 here. At 4 what are the processes available here? P1 is there, P2 is still there. Then we have a new process P4 with 8 burst time. Now non-preemptive SJF will pick up the shortest job from this list. So P4 is the shortest job here. So the next executing job will be P4. So for how long? For 8 burst time. 4 plus 8 will give you 12. Now we have to see at 6 arrival time we have P5 process, but at that time P4 was executing. It is not interrupted by any newly arrived process because they have mentioned it as non-preemptive. So here at 12 what we can do? P1 is 9, P2 is 30 and now we have P5 with 11. Now which is the shortest job next? It is P1. So we will go with P1 and it will be executed for 9 burst time. 12 plus 9 will give 21. At 21, what are the processes remaining? P2 with 30 burst time and P5 with 11 burst time. Which is the shortest job here? P5. So P5 will be executed for 11 burst time and it will end up at 32. At 32, the only process that is available will be P2 with 30 burst time. So P2 will be executed in the last with 30 burst time, means it will get completed at 62. The first question is for non-preemptive SJF. Which is the second last to be completed? It is P5. Now I have taken non-preemptive SJF with P5 as the answer. There are two options matching, so we can rule out 1 and 3. Now we will go with the next algorithm, that is round robin. Round robin is a CPU scheduling algorithm in which each process is assigned a fixed time slice called time quantum and the CPU cycles through all ready processes in a circular order, giving each one a fair and equal share of processing time. This ensures no process is starved. So here the time quantum is 10. Here t is equal to 10, here t is equal to 10 and here t is equal to 10. So this is round 1, round 2 and round 3. We will start from 0 here. At 0 we have 3 processes, P1, P2 and P3. So initially it will start with P1. So let's take P1 here and in round 1 we have P1. P1 will be executing for 9 burst time, but the total time quantum that is available is 10. So it will take 9 burst time and so it completes at 9. At 9, all processes will go for first round of the quantum. So the second process that will enter the CPU will be P2. This is at time 9. We have P2 and P3. At that time even arrival time 2 P4 process and arrival time 6 P5 process will be available. So we have 4 processes remaining. Now P2 will take the CPU. P2 will run for 10 burst time. So now just calculate 10 from 9, it is 19. P2 will run. So for how long it has run? It has run for 10. P2 has a burst time of 30 and in that 10 burst time is done in round 1. So what is the remaining time for P2? It is 20. At 19, P2 has finished execution, so it will move to the last in the circular order. P3 will be standing first, P4, P5 and then P2 will be joining here with 20 burst time. Now what is the burst time of P3? It is 4, P4 is 8 and P5 is 11. Now let's go for the next process, that is P3. P3 has 10 time quantum, but what is the total burst time? It is 4. Since it is having only 4, 19 plus 4 will give 23 and P3 will complete execution. So at 23, now we have P4 with 8 burst time, P5 with 11 burst time and P2 with 20 burst time. Now we have P4 here. This will run for 8 burst time. 23 plus 8 will give 31 and it is P4's turn. Now at 31, we have P5 with 11 burst time, P2 with 20 burst time. Now P5 will run for 10 burst time. This will end up with 41. This is P5 process. At 41, P5 has run for 10 burst time and remaining 1 is there. P2 has remaining 20. But once P5 has finished execution, it will move in the circular order next to P2. So the order will be P2 will be having 20 and P5 will have remaining 1 execution time. All the 5 processes have completed round 1 of execution. In that P1, P3 and P4 have completed execution totally. What are the remaining processes here? P2 and P5. In round 2, P2 will take 10 burst time again. It has 20 burst time altogether. It will take 10 burst time now. So now we will have 10 remaining here. So P2 will be executing till 51. So at 51, what happens? P2 will enter after P5 in the next circular order. P5 will have remaining 1 burst time and P2 will have 10 burst time. So now P5 will execute for 1 burst time in the second round and so we'll go with 52. This is P5 and now P5 is getting completed. So at 52, the only process that is remaining will be P2 with 10 burst time. When it enters round 3, P2 will also get completed with the final 10 burst time. So P2 is the final process here. The process completion time is 62. Just read the question. Which of the process shall finish second last? So when you take the completion order, P2 is completing last. Which is second last? P5 is again second last even in round robin, similar to non-preemptive SJF. So RR will have P5 as the answer. Option 2 will also be ruled out and we will go with option number 4. P5 is the second last in SJF and P5 is the second last in round robin algorithm. I hope you understood the round robin execution. For the first round, all the processes will be allowed inside in order based on the arrival time, and for the second round, whichever process is incomplete with the remaining burst time, they will be entering in the same order. Say for example, when P2 is getting executed here at 9, once it finishes its time, it will go and sit next to P5. That's what they say. it will cycle through all processes in circular order. Again, when P5 completes, you will be given a chance in round 2. Once it completes round 2, the second time quantum, again it moves next to P5 and waits for its third round. So in the third round only P2 is getting completed. Now just check the burst time. 10 plus 10 plus 10. The 30 burst time is split into 3 rounds. Just take P5, 10 plus 1. It is split into 2 rounds. So this is how we will be working with round robin and non-preemptive SJF. Next question. Which of the following statement is correct for Pthreads? The correct POSIX standard for Pthreads is IEEE 1003.1c and not 1002.1c, which is wrong. So 1 is not the answer. This standard defines API for thread creation only, states the second statement. The Pthreads API defines functions for thread creation, termination, synchronization. Mutex's condition variables are involved and other thread management operations. It is not defined only for thread creation. So 2 is also ruled out. Let's take the third statement. This is a specification only for thread behavior and not its implementation. Pthreads defines a standard API for thread related operations, outlining how threads should behave and be managed. It does not dictate the specific internal implementation details of how an operating system achieves this behavior. Different operating systems can implement the Pthreads API in their own ways while adhering to the specified behavior. So, the third statement is perfectly correct. This is a specification only for thread behavior and not its implementation. They say it does not dictate the specific internal implementation details. What about the fourth statement? Operating systems like Solaris, Linux, Mac OS X except True64 Unix implement Pthreads. True64 Unix also implements Pthreads. It supports a 2-level threading model which allows user level threads to be bound to kernel level threads. So this is also false. Actually, Solaris, Linux, Mac OS implement Pthreads. They have told this particular True64 Unix as exception, but there is no proof that they have not implemented Pthreads. So it will also implement Pthread is the statement that we can infer from that. Option number 3 will be the right answer. Next question. What shall be the average waiting time per process? If we know that 10 processes on average arrive every second and there are normally 20 processes in the queue. This question will need a new information that was not used in any of the previous year question paper. To calculate the average waiting time per process, we use Little's law, a fundamental principle in queuing theory. L is equal to lambda into W. L will be the average number of items in the system, that is the queue length. Lambda will be the arrival rate, items per unit time, and W will be the average waiting time in the system. So we have to find W. So W is equal to L divided by lambda. L is equal to average number of items. So average number of processes in the queue. Average number of processes in the queue is given as 20 processes. That will be capital L. Lambda will be arrival rate. 10 processes arrive every second. So 10 processes per second will be the lambda value. Now we have to calculate W. So W is equal to L divided by lambda. L will be 20 processes divided by 10 processes per second. This per second will move to the numerator. Processes will go. 20 divided by 10 will give you 2. So the answer will be 2 seconds. 2 seconds will be the average waiting time in the system. Option number 2 will be the right answer. This is a typo here. Next question. What is the total swap time? Swap in and swap out together will give you total swap time. In a system for a 15 MB process, megabyte process with a transfer rate of 30 megabytes per second. See the unit carefully, it is megabyte and megabyte. Given that there is an average latency of 12 milliseconds, however, no headseeks involved. They are asking for the total swap time. Now we will just see what is the swap in time formula. Process size divided by transfer rate plus latency. So this has to be calculated first and then you have to add latency. What about swap out time? It is the same formula. Then how will we take total swap time? It is swap in time plus swap out time, or you can take it in other way as twice the swap in time or twice the swap out time, because both are going to give you the same formula. From the question we will take two details. Process size is equal to 15 MB and the transfer rate is given as 30 megabytes per second. And the latency value is given as average latency of 12 milliseconds. So latency will be 12 milliseconds. Since it is in MB and MB, we need not touch it, but here it is per second and here it is milliseconds. So in order to convert this into seconds, latency can be taken as 12 into 10 to the power minus 3 seconds. This will be the latency value to keep it in the same unit. Now let's take the total swap time. The process size will be 15 megabytes. The transfer rate will be 30 megabytes per second along with the latency 12 into 10 to the power minus 3 seconds. So this is 1 by 2. Megabyte will get cancelled and this seconds will move to the numerator plus 12 into 10 to the power minus 3 seconds. Both are having same units, seconds. 1 by 2 can be written as 0.5 seconds plus 12 into 10 to the power minus 3 can be written as 0.012 seconds. 2 into what is 0.5 plus 0.012? It is 0.512. So this is 0.512 seconds. And when you multiply it by 2, you will get 1.024 seconds. This will be the total swap time. So the swap in time will be 0.512 seconds. The swap out time will be 0.512 seconds. And the total swap time will be these two time taken together. So option number 1, 1.024 seconds will be the right answer. Next question, consider the following interrupt protection levels in Linux and arrange them in the increasing order of their priorities. This question has been previously asked in one of the previous year question paper. Interrupt protection levels in increasing priority are given here. User mode programs that are preemptible, kernel system service routines that are preemptible, bottom of interrupt handlers and top of interrupt handlers. This will be A from the question, kernel system will be D, bottom half will be B and top half will be C. They are asking in increasing order of priority where the order should go from bottom to top as per the question and as per the diagram also it is the same. So the order will be A, D, B, C. Option number 4 will be the right answer. Linux implements architecture by separating interrupt service routines into two sections, top half and bottom half. Top half will be the standard interrupt service routine that runs with recursive interrupts disabled. Interrupts of the same number are disabled but other interrupts may run. The bottom half is run with all interrupts enabled by a miniature scheduler that ensures that the bottom halves never interrupt themselves. The bottom half scheduler is invoked automatically whenever an interrupt service routine exits. So top half will be running with all recursive interrupts disabled while the bottom half will have all interrupts enabled. This is one extra point that you can learn here. Each level may be interrupted by code running at a higher level but will never be interrupted by code running at the same or lower level. So when you take increasing priority, this will be the most prioritized part. Here they say every level will be interrupted by code running at a higher level. It means when C has to do something, it can interrupt B, but it can never be interrupted by code running at the same or lower level, means B cannot disturb C. So they say whether it's same or lower level, it can never be interrupted. But for user mode code alone, they are saying user processes can be preempted by another process when a time sharing scheduling interrupt occurs. So the exception is given to this part. Next question, which of the following shows the correct hierarchy of a layered file system in an operating system? So let's see the hierarchy. Application programs, logical file system, file organization module, basic file system, IO control and devices. So A, logical file system, B, file organization module, C, basic file system, D, IO control. Application programs is E. So this is the hierarchy top to bottom. So the order will be E, A, B, C, D. This is available in option number 3. Option 3 will be the right answer. File system provide efficient and convenient access to the disk by allowing data to be stored, located and retrieved easily. Now we'll see about the layered file system terms. IO control level consists of device drivers and interrupt handlers to transfer information between the main memory and the disk system. So devices are here. And what about the basic file system? It needs only to issue generic commands to the appropriate device driver to read and write physical blocks on the disk. What about file organization module? The file organization module knows about files and their logical blocks as well as their physical blocks. Finally, the logical file system manages metadata information. If you get into the reference book, you will have lots of detail, but this is just like an introduction to all the terms that are present here. Next question, once the process is allocated CPU and executing, which of the following events could not occur? Let's see the A statement. The process could issue an IO request and then be placed in the ready queue. B states that the process could create new subprocesses and wait for the termination of the subprocesses. C states the time slice of the process expires and it may join the waiting queue. When you take scheduling, they are saying the time quantum when it is over, it will join the waiting queue. What about D? The process is forcibly removed from the CPU and is put in the waiting queue due to the arrival of an interrupt. So these are the key terms that you have to take from the statements. Now we will see every statement. When a process issues an IO request, it cannot continue execution until the IO completes. It is moved to the waiting queue and not the ready queue. This queue is wrong. It will be moving to the waiting queue. They say it is blocked here because it is waiting for an IO to be completed. Once that request gets completed, it will continue execution. Ready queue is for processes that are ready to run but waiting for the CPU time. Only when the CPU is not available, only when it needs time from the CPU, it will be pushed to the ready queue. So this statement is giving clue for another statement here. So from this we can say that A is definitely wrong, and here they are asking which cannot occur. So A cannot occur. Any option that does not include A can be ruled out. Always see what they are asking. Next, B. Parent process can spawn. Spawn means it can create child processes and wait until they finish. This is common in multitasking system. So B is definitely true. In this question, B cannot be taken as the answer. So I am just marking right and wrong and then we will go with the options later. What about C? When a process time slice expires in preemptive scheduling, it is not waiting on any resource. When it is waiting for any resource like IO or something, it will move to the waiting queue. If it is not waiting for any resource, it is moved to the ready queue and not the waiting queue. So here it is wrong. It has to move to the ready queue. So this is also wrong. The waiting queue is only for processes that are blocked due to I/O or other events. C is also wrong. What about D? An interrupt may cause the process to be preempted, but it is typically moved to the ready queue, not the waiting queue. Here also it is moving to the ready queue and not to the waiting queue. The waiting queue is reserved for processes that are blocked, not simply interrupted. It is blocked for I/O or other events they have mentioned. Only if the interrupt triggers a blocking operation like I/O, the process would go to the waiting queue. So D is also wrong. So just for clarity I am writing B will occur. A, C, D will not occur. So the question is about which will not occur. So we can even rule out option 3 because A, C, D are involved here. Option number 4 will be the right answer. So understand, when there is I/O request, it will enter the waiting queue. When the time slice expires or when there is an interrupt, both will be taken to the ready queue and not the waiting queue. Next question. Identify the correct statement from the following with respect to Spinlock semaphores. Let's see the statements now. The name refers to busy waiting semaphores. So here they are asking for correct statements. B states they are not useful when the locks are to be held for a short duration of time. C states it may require multiple context switches when a process waits on a lock. D states they are often employed on uniprocessor systems. Now we have to check which are right. Let's start with A. A spinlock is a synchronization mechanism where a thread spins in a loop, continuously checking if the lock is available without giving up CPU control. This is known as busy waiting, and it's the defining characteristic of spinlocks. The name refers to busy waiting semaphores is perfectly true. What about B? Spin locks are most efficient when the lock is held for a very short time. They are actually useful, so the statement is wrong. The overhead of a context switch is avoided, making spin locks ideal for quick operations. If the lock is held for a long time, spin locks waste CPU cycles and are inefficient, so it is perfectly useful for short time and not for long time. They say when it is held for a long time, spin locks are wasting the CPU cycles and so it becomes inefficient. What about C? Spin locks do not involve context switches because the thread keeps running and polling the lock. In contrast, semaphores do cause context switches when a thread blocks and the scheduler switches to another thread. So here they say spin locks do not involve context switches. So this is also wrong. What about D? Spin locks are not ideal for uniprocessor systems. They say they are often employed on, which is totally wrong again. Since only one thread can run at a time, a spinning thread wastes CPU cycles while the lock holder cannot proceed. Spin locks are better suited for multiprocessor systems where one thread can spin while another releases the lock. So what is thread spinning here? Thread spinning in a loop is continuously checking if the lock is available without giving up CPU control. If there is only one processor and that processor is going to concentrate on this particular part, then which thread will release the lock? So in that case, it is suited for multiprocessor system and it is not ideal for uniprocessor system. Only A is correct here. So option number 1, A only will be the right answer. So we will rule out 2, 3 and 4 here. Next question, we have matching list, clustered page table, hierarchical page table, segmentation, inverted page table. Clustered page tables group multiple pages into a single entry, reducing overhead. This is especially helpful when large portions of the virtual address space are unused. When large paths are unused and only certain paths are used, this will create a sparse look. You could have come across the term sparse matrices. Many entries will be 0, only few entries will be non-zero. Similarly, non-zero entries can be taken where you have entries. The large portions that are unused can be taken for 0 entries in that matrix. So here clustered page table is useful for sparse address spaces. A will be mapping to 3. A3 is available in 2 of the options. What about hierarchical page table? 64-bit systems have massive address spaces. Hierarchical means multi-level page tables grow too large and complex. Managing multiple levels of page tables becomes inefficient and memory intensive. So we will go with generally considered inappropriate for 64-bit architectures because they say managing multiple levels becomes inefficient and memory intensive. So this is equivalent to saying it is inappropriate. B will be mapping to 1. B1 is available in option 2. We can even rule out option 1. The next one is segmentation. Segmentation divides memory into logical units like code, data and stack. This aligns with how users and programmers think about memory, offering protection and modularity. So segmentation will be supports a user view of the system. They say this aligns with how users and programmers think. So C will be mapping to 4. What about inverted page table? Unlike traditional page tables which map virtual pages, inverted page tables map physical frames. There is one entry per physical frame, making it memory efficient for large systems. Has only one entry for each real page or frame of memory. D will be mapping to 2. Option number 2, A3, B1, C4, D2 will be the right answer. Next question. This is about RAID levels and this has been quite a very repeated question in the previous year question papers. So let's get into the diagram. RAID level 2 is memory style error correcting code. A will be mapping to 4. A4 is available only in one option. RAID level 3 is bit interleaved parity. B is mapping to 3. RAID level 5 is block interleaved distributed parity. C is mapping to 1. RAID level 6 is P plus Q redundancy. So D will be mapping to 2. We have C1 and D2 also. Option number 1, A4, B3, C1, D2 will be the right answer. So it's better you have an idea from RAID 0 to RAID 6 levels and also have an idea about what is happening in every level so that it will be helpful for you in some other question paper. Now we are entering into the comprehension type of question where 5 questions depend on this particular part. Consider the following disk queue with request for I/O to block on cylinders 45, 81, 185, 33, 175, 99, 150, 77. Consider that the head starts from location 58. Let's see the first question. What shall be the total head movement of cylinders if the FCFS disk scheduling method is used? So let's take the cylinder arrangement here. They say it starts from location 58. I have placed the request 33, 45, 77, 81, 99, 150, 175 and 185. What is FCFS? First come first serve. Processes disk request in the order they arrive. So from 58 the first request will be 45. From 45 it will move to 81. From 81 it will go to 185. From 185 it will go to 33. From 33 it will move to 175. From 175 it will move to 99. From 99 it will move to 150. From 150 to 77. So we are just using the same order that is given in the question. That is the purpose of FCFS. In whichever order they arrive, it will be processed in that way. Now let's take the difference between 58 and 45 to be 13. Then 45 and 81 will be 36. 81 and 185 will be 104. Then we have 185 and 33 to be 152. The difference between 33 and 175 will be 142. Then 175 to 99 will be 76. 99 to 150 will be 51. 150 to 77 will be 73. When you add up all these, you will get a value of 647. This will be the total head movements of cylinders when we use FCFS disk scheduling method. Option number 3, 647 will be the right answer. Next question. What will be the total head movement of cylinders for the SSTF disk scheduling technique? The head starts from location 58. What is SSTF? Shortest seek time first. This selects the request which requires the least disk arm movement from its current position regardless of the direction. So from 58 we have two possibilities. 77 minus 58 will need 19 movements and 58 minus 45 will need 13 movements. Which is short here? 13 is short. So from 58 we will process 45 next. Again from 45 you have two options, 33 and then 77. 45 and 33 will need only 12 movements, while 45 and 77 will need 32 movements. So we are going with 33. From 33, the next request that has to be processed will be 77 only. After 77 it is 81, after 81 it is 99, after 99 it is 150, after 150 it is 175, after 175 it is 185. So now let's calculate the total head movement. Total head movement is equal to 58 and 45 will have 13 movements, 45 and 33 will have 12 movements, 33 and 77 will have 44 movements, 77 and 81 will have 4 movements, 81 to 99 will be 18, 99 to 150 will be 51, 150 to 175 will be 25, 175 to 185 will be 10. Altogether, we will have 177 head movements. This is available in option 3. Option number 3 will be the right answer. Next question. What shall be the second request being processed by scan left disk scheduling technique for the already given request queue? Actually, when you take scan algorithm, scan moves in one direction. It can be either left or right, servicing all requests along the way. Once it reaches the end of the disk, it reverses direction and continues servicing request in the opposite direction. This is scan algorithm. Since they have mentioned scan left, we can take it like when the direction is set to left, the disk head moves from its current position towards the lower numbered cylinders servicing request along the way. So let's take the cylinders here. The current position is 58. This is left and this is right. So when they say it moves to the left, that is scan left. When it is set to left, it is moving towards the lower numbered. Compared to 58, 45 and 33 are lower numbered. 77 and all are higher number. So it is moving towards the lower numbered cylinders is what they say. So from 58, the first request will be for 45 and the second request will be for 33. What is the question here? Second request being processed by scan left. If this is going to be the first request, what is the second request? 33 will be the second request. Option number 3, 33 will be the right answer. So after finishing 33, once it reaches the end of the disk, means it will come to this particular end, it reverses direction and continues servicing request in the opposite direction. So we are not getting into detailed scan algorithm now. There are already previous year question papers that explains scan algorithm better. So for this question alone, I am just giving you the answer. Next question. What shall be the total head movement of cylinders for the C-scan disk scheduling technique if the head starts moving in the right direction from the initial position? What is C-scan? The disk head moves in one direction only. As per this question, it is given right side. So we are taking right. It services all requests along the way until it reaches the end of the disk. Once it hits the end, it jumps back to the beginning of the disk without servicing any request on the return trip. So take this to be one end and the other end. After it hits this particular end, it will come back to the beginning without servicing anything on the return trip is what they say. No service will occur during the return trip. Now let's get back to the arrangement. The head position is in 58 and we have to move to the right side. Here they are talking about end of the disk. Any disk cylinder will start from 0. Since it has gone till 185, so we can take 199 to be the end here. There are totally 200 cylinders. We are taking 0 to 199 as the range. Now from 58 we have to move towards right. 58 to 77. So let's calculate the total here. The difference is 19. From 77 it is 81. It is 4. 81 to 99 is the next request. It has 18 movements. From 99 we move to 150. There are 51 movements. From 150 we are moving to 175. 25 movements. From 175 to 185 it is 10 movements. From 185 it has to reach the end of the disk, which is 199. The difference is 14 here. From 199 it has to jump back to the beginning of the disk, which is 0. What is the total number of movement? 199 movements are involved. Just returning back to the beginning of the disk without servicing any request. After it comes to 0, it will service the request again in the right direction. So from 0, the first request will be 33. So the movements will be 33. From 33, it will process 45 next and the movements will be 12. When you add all the movements together, you will end up with 385 as the total head movements. Option number 4 will be the right answer. So it will start from the right, it will go till 185. From 185, it will reach the end of the disk. That is 199. From 199, once it hits the end, it jumps back to the beginning is, it will move to 0 without servicing any request. That's why the whole movement, now 199 minus 0 will give you 199 movements are counted for the total head movement. It will again start servicing the request once it reaches the beginning. So it is servicing 33 and 45. Next question. What shall be the second request being processed by CLOOK write disk scheduling technique for the already given request queue? In CLOOK, the disk head moves in one direction only. For this question, we are taking right. It services all requests in that direction until it reaches the last request. Instead of going to the end of the disk, instead of going to 199, it jumps directly to the lowest number pending request and continuous servicing in the same direction. Now the question is, what shall be the second request? So the current head position is 58 and it has to move in the right direction. The first request that is being processed will be 77 and the second request will be 81. Option number 1, 81 will be the right answer. You just need to find whatever is asked in the question and then move out of the question to save time. Don't keep working for total head movements in CLOOK as well as in scan question and waste your time. Just answer whatever is being asked and then move. I already explained CLOOK and scan algorithm in previous year question paper. That's why I am not working on it in this particular video. If you want to know how that particular algorithm works for calculating total head movements, I would suggest you to go and watch the previous year question paper solutions video in order to understand how that process is happening. With this, we are completing Unit 5 questions.